In previous videos, we covered some of the basic materials, including the basics of vectors, inner product of vectors, and the orthogonal vectors. And then we extended the concept and we talked about the inner product of functions and the orthogonal functions. In the last video, we introduced the concept of orthogonal sets. Now in this video, I'm going to talk about the infinite sets, and in the next following videos we're going to cover the concept of norm and square norm of a function and the orthonormal sets, and after that we're going to be talking about the orthogonal series expansion, which is going to be pretty much all the basic materials that we wanted to cover for the partial differential equations course. So here is the structure for the rest of this video. I'm going to have a short recap on the concept of orthogonal sets, and then I'm going to define the concept of infinite sets, and then we're going to have a important discussion on the significance of this infinite set. Why do we really care about infinite sets? And at the end, I'm going to be providing you with some practical examples. We're going to be looking at some of the infinite sets, and you're going to see later that they're going to be really useful and important when it comes to the Fourier series. Let's start with a quick recap on orthogonal sets. Remember, we said a set of real valued functions like phi1, phi2, phi3 all the way to phi n is called orthogonal on the interval a to b if each pair of the functions like phi I and phi j is orthogonal on that given interval. So that means if you have a set of functions like phi1, phi2, phi3 all the way to phi n, then for each pair of functions that you can pick from this set, for example phi1 and phi2 or phi1 and phi3, etc., right? For each of these pairs of functions, if the pair of function is orthogonal for all of those pairs of functions, then you would call this set to be orthogonal, right? And we also said that two functions are called orthogonal whenever their inner product is 0. So for example, phi1 and phi2 is called orthogonal when their inner product, phi1 and phi2, equals 0, right? And similarly, for example, phi1 and phi3 are going to be orthogonal if their inner product is 0, right? And by definition, you remember that we said that the inner product of two functions like phi I and phi j is just the integral of their product, phi I times phi j, over that given interval. So for example here, over the interval a to b. So, and when we say that two functions are orthogonal, again their inner product is simply 0, which means that this integral is 0. And if that's the case for any pair of functions that you can imagine in this set, then this set itself is going to be called an orthogonal set. Now let's discuss the infinite sets. As you will see in future, we are mainly interested in infinite sets of orthogonal functions. That means we most often work with the sets consisting of infinite number of orthogonal functions. For example, phi1, phi2, phi3, phi4, etc. And you may ask, why is that? Why is it important for us to have infinite sets of orthogonal functions? And to answer that question, we can resort to the analogy between vectors and functions. So let's consider a two-dimensional space. We can visualize that using this coordinate plane with the x and y axis, and we know that we can have a basis for this two-dimensional space using the orthogonal vectors of I and j, and any other arbitrary vector that you can imagine in this two-dimensional space can be generated using a linear combination of these members of the basis I and j. For example, if you have this vector a with components of 5 and 2, you can generate that as 5i plus 2j, right? So you can use this basis that you have here, I and j, to generate this vector a. Similarly, if we go to the three-dimensional space, we can have a basis consisting of three orthogonal vectors like I, j, and k. And then any arbitrary vector like a can be generated using a linear combination of these members that you have in your basis. So for example, this vector here with the components of -3, 2, and -4 can be produced using this specific linear combination of I, j, and k. So it can be written as -3i plus 2j minus 4k. We can then generalize this concept and we can go to infinite dimensional space. And if we do so, then we need to have a basis consisting of infinite number of vectors, orthogonal vectors, like e1, e2, e3, etc. And then any arbitrary vector like a with the components of a1, a2, a3, etc. can be generated using a linear combination of all these vectors that you have in your basis. For example, a can be written as a1, e1 plus a2, e2 plus a3, e3, etc. So the key then is to have a standard basis with infinite number of orthogonal vectors in it. Now let's get back to the context of function. So if you have a function like f of x defined on the interval a to b, you can represent this function in a vector fashion, in a infinite dimensional space. And the way that it works is that you can look at the interval a to b and you can represent that using a vector with infinite coordinates. For example, the first coordinate is going to be a, and then from a to the to x1, for example, from here to here, you're going to have infinite points. Each of those points can be one coordinate of this vector. So you're going to have a as the first component, and then after infinite number of coordinates, you get to the x1, and then similarly you're going to have infinite number of points between x1 and x2, and after that you get to x2, and similarly you can keep going until you get to the last point of this interval, which is b. So you're going to have another infinite number of points, number of coordinates in this vector until you get to b. So x can be thought of as a vector in the infinite dimensional space. Now you can think of another vector like f, which is just an infinite dimensional vector, each component of which is just the value of function f of x acting on that given coordinate that you get from vector x. For example, the first component of f is going to be f of a, and then you're going to have infinite number of components until you get to x1. So the value of the function acting on x1 is going to be f of x1. Similarly, you will get f of x2, and at the end f of b, right? So f is also a vector in the infinite dimensional space. So the key point here is that the continuity of the interval a to b allows us to represent this function as a vector in the infinite dimensional space. So now let's step back and see what we have so far. So from the vectors context, what we have is that if you have an infinite dimensional space, you need to have an infinite set of orthogonal vectors, and that infinite set will allow you to generate any arbitrary vector that you have in that infinite dimensional space, right? And on the other side, we said that functions, continuous functions, can be thought of as vectors in infinite dimensional space. So the conclusion is that in the context of functions, we are dealing with infinite dimensional space. So we are dealing with R infinity, and that means that we need to have an infinite set, an infinite basis to generate any arbitrary function. So we need to have a basis with infinite members, like a vector here, the first vector, which is a representation of a function like phi x, phi 1x. The second vector in the infinite dimensional space, which is a representation of another function like phi 2 of x, and then phi 3 of x, and so on and so forth. And then using all these functions, which can be thought of as infinite dimensional vectors, similar to the vector context, we can then generate any infinite dimensional vector like f. So again, this f can be thought of as a vector like f of a all the way to f of b, right? Any vector like f can be generated using a linear combination of all these vectors that we have in our basis. And when I say these vectors are in infinite dimensional space, so they are representation of corresponding functions like phi 1, phi 2, phi 3, and so on and so forth. So then getting back to the context of functions, any function like f can be written as a linear combination of all these functions that we have in our basis, phi 1, phi 2, phi 3, etc. So then as a recap, since we are dealing with a function that can be represented as a vector in the infinite dimensional space, we need to have a basis that consists of infinite number of orthogonal functions. That's the key point here. So now let's take a look at an example here. So we have this infinite set shown here, and we want to prove that this infinite set is orthogonal on the interval minus pi to pi. So how can we prove that? So the first thing to note here is that this set is an infinite set, meaning that it has infinite number of functions. And the reason is that you have cosine x, cosine 2x, cosine 3x, and so on and so forth. So how can we find all the pairs of functions in this set and then find the inner product of all those pairs? So since we have infinite members in this set, so we have infinite pairs as well. How can we calculate the inner product for all those infinite pairs of functions? To clarify, so one pair of functions is going to be 1 and cosine x. The other one is going to be 1 and cosine 2x. We have also 1 and cosine 3x, and so on and so forth. So
That's one kind of class of pairs of functions. The other one is going to be, for example, cosine x and cosine 2x, cosine x and cosine 3x, and so on and so forth. So we have infinite pairs of functions here, and we want to calculate the inner product of each of these pairs of functions. So the solution for this problem is that we can write all these functions that we have here as a class of cosine nx, in which n varies from 1 to infinity and is going to be an integer of 1, 2, 3, and so on and so forth. So cosine nx is going to be representing all these functions that we have here. Cosine x is going to be what you would get by substituting n equals 1 in here. If you have n equals 2, then you would get cosine 2x. If you put n equals 3, then you would get cosine 3x. So in this way, then we represent this infinite set in a kind of simpler form. So right now, by doing this, we have just two classes of functions. One of them is just 1, so this class has just one member, and the other class is cosine nx with infinite numbers. So what is the advantage of doing this? So by classifying all these functions into two classes of 1 and cosine nx, our job is going to become much more easy. So we just need to find the inner product of 1 and any member of cosine nx, which is going to be this scenario. So the inner product of 1 and any member of cosine nx for n equals 1, 2, 3, etc. So that means you can have 1 as one of the functions and cosine x, for example, as the other function. So then you would need to find the inner product of 1 and cosine x. Similarly, you can have 1 and cosine 2x, or you can have 1 and cosine 3x. All these pairs of functions are going to be represented by 1 and cosine nx. But the other scenario that you could have is to have both of functions coming from cosine family. So one of them can be, for example, cosine x, the other one can be cosine 2x, or cosine x and cosine 3x, or cosine 2x and cosine 3x, and so on and so forth. So we have basically two scenarios. The first one was the case that you have 1 as one of the functions, and the other function is coming from cosine nx family. And the second scenario is that both of the functions are coming from this family of cosine nx. But be careful, two functions that we pick are going to be distinct, because we want to see if those two distinct functions are orthogonal or not. So then we consider one of the arguments to be nx, the other one to be mx, and is not the same as m, right? Meaning that one of the functions can be cosine x, the other one cosine 2x. Or one of them can be cosine x, the other one cosine 3x, and so on and so forth. We're not interested in inner product of a function with itself. So now you can see that by classifying all these functions into some proper categories, our job has become much simpler. We just need to find two inner products, basically. One and cosine nx, and the other one is going to be cosine nx and cosine mx. And if we do that, then these two inner products are going to be representing all the infinite number of inner products that you could imagine for this infinite set. So let's consider the first category in which you have 1 and cosine nx. And we want to find the inner product of these two functions. One of them is 1, and the other one is cosine nx, which can be cosine x, cosine 2x, cosine 3x, and so on and so forth. And so from the definition, the inner product of these two functions is going to be the integral of the product of these two functions. So integral 1 times cosine nx dx, and the interval is minus pi to pi. So minus pi to pi is going to be the lower and upper bounds of this integral. And if you do the calculation, it's going to be just integral cosine nx dx from minus pi to pi. And if you integrate this, it's going to be 1 over n sine nx. So from minus pi to pi. And if you substitute minus pi and pi into this relation that you have here, you're going to get sine n pi minus sine minus pi. So feel free to pause the video here and think about why these terms are 0. But basically, if you have an integer like 1, 2, 3, 4, etc., and if you multiply that by pi, the argument that you get there, the sign of that is going to be 0. So in other words, if you have sine of pi is going to be 0, sine of 2 pi is going to be 0, sine 3 pi is going to be 0. All of them are going to be zeros. And similarly, the minus 1 times each of these arguments is going to have the same results, meaning that sine of minus pi is going to be 0, sine minus 2 pi is going to be 0 too, sine minus 3 pi is going to be 0 as well. So at the end, we're going to get a 0 for this whole inner product. And just as a reminder, we have not just calculated one inner product here. What we have obtained is the inner product of infinite pairs of functions. 1 and cosine x, 1 and cosine 2x, 1 and cosine 3x, and so on and so forth. Now let's look at the second scenario that we could have. In this scenario, both of functions can come from the cosine nx family. So the first one, let's consider that cosine nx, and the second one cosine mx. And we want to find the inner product of these two functions. So by definition, the inner product is going to be just the integral of the product of these two functions, cosine nx, cosine mx, over the interval that we are interested in, which is minus pi to pi. So the way to deal with this integral is just to use the trigonometric identity that we have shown here. So we have two cosines, right? So if you look at this identity, cosine alpha times cosine beta can be written as the summation of two cosine functions. And if we use this identity, then we can rewrite this integral as this one. So it's going to be the same integral minus pi to pi, but here we have cosine this argument plus this argument, which is going to be nx plus mx. We can write it as n plus m times x plus cosine alpha minus beta. You see, so this argument minus this one. So it's going to be nx minus mx, which is going to be n minus m, this whole term, times x. Right? And then this whole expression divided by 2. Now it's going to be easier to evaluate this integral because we can break it down into two integrals. The first one is cosine n plus mx, which is shown here. And similarly for the second one, we have half times integral minus pi to pi of this term, which is cosine n minus mx. So now we are dealing with just two simpler integrals. So the first one, if you evaluate this integral, is going to be sine of n plus mx divided by n plus m. And we have a factor of half here, which shows up here, from minus pi to pi. For the second one, we're going to have integral cosine n minus mx, which is going to be sine of n minus m times x divided by n minus m. And we have a factor of 1 over 2 from here. So from minus pi to pi, and if you substitute pi and minus pi into this equation and subtract from each other, you get this equation. So from the first term, you're going to have sine n plus m, substituting pi is going to be n plus m times pi minus sine of now minus pi. Substituted here is going to give us minus n plus m times pi divided by this factor, which is a constant. Right? And for the second one, we're going to get sine n minus m, and then pi is going to be substituted here. It's going to show up here, sine of n minus m times pi minus sine of n minus m. Now minus pi is going to be substituted. So it's going to be sine of n minus m times minus pi, which is going to be this term here, divided by this constant we have here, 2 times n minus m. So again, we have an integer multiplied by pi. Regardless of the value of that integer, we know that sine of that value, that argument, is going to be 0. So this term is going to be 0 then, this term is going to be 0, these two terms are going to be similarly 0 too. And at the end, we're going to get 0 for the whole expression. So that means this inner product that we evaluated is going to be 0 for any n and m, basically, as long as they're not equal. So if n is different from m, then for any pair of n and m that you choose from the positive integer values of 1, 2, 3, etc., this inner product is going to be 0. So now we have considered both of the scenarios that are possible, and we know that for all those infinite number of pairs of functions that we can imagine from this infinite set, the inner product is going to be 0. And that basically means that this infinite set is orthogonal on this interval of minus pi to pi. Now let's look at another example which is a little bit more complex. We have this infinite set shown here, and we want to prove that this infinite set is orthogonal on the interval minus L to L. So we have one function here, which is just 1, and then we have infinite number of functions here: cosine pi x over L, cosine 2 pi x over L, cosine 3 pi x over L, and so on and so forth. And then we have another set of functions with infinite members: sine of pi x over L, sine 2 pi x over L, sine 3 pi x over L, and so on and so forth. So similar to the previous example, the most effective way to calculate all those infinite number of inner product of the pairs of functions is to classify all these functions that we have here in a proper fashion. So the first class is going to be just 1 itself. The second one is going to be a formula that represents all these cosine functions, and that's going to be cosine n pi x over L, right? And n is going to be an integer, a positive integer, 1, 2, 3, etc. And similarly for the second set, we can have sine of n pi x over L. I should say m, since these n and this m can be independent. You can have cosine 2 pi x over L, but you can have sine 1 pi x over L. So we have two integers here, m from 1 to infinity basically. Now it's much easier to find all the scenarios that you could imagine for two distinct functions to be picked from this infinite set, and then calculate the corresponding inner product of those two functions. So now let's see what scenarios we can have. So we have three classes of functions. The first one is going to be just 1. The second one is going to be cosine of an integer times pi x over L. And the last one is going to be the class of sine functions, sine of an integer times pi x over L. So the scenarios that we could imagine here is going to be as follows. We can have 1 and one of the functions from the cosine family. So it's going to be these two classes. And then the inner product for that is going to be inner product of 1 and cosine n pi x over L, and equals 1, 2, 3, etc. The second scenario is going to be the case that you have one of the functions to be 1 and the other one is going to be picked from the third class, the sine class. So we're going to have 1 and sine of an integer times pi x over L. And that's going to be the second scenario that we have, the inner product of 1 and sine of an integer times pi x over L, wherein that integer is going to be 1, 2, 3, etc. So the next scenario is going to be the case that you pick one of the functions from the cosine family and the other function from the sine family. So for that, you're going to have the inner product of cosine 1 integer times pi x over L and sine of an integer and completely independent integer times pi x over L. So for this scenario, n and m are positive integers and they can be even equal. So because they're coming from two different classes, two different families, right? So you can have, for example, cosine 1 times pi x over L and sine of 1 times pi x over L, right? So that's the third scenario. The next one is going to be the scenario in which you pick both of the functions from this cosine family. So for this scenario, you need to have two distinct functions, right? You cannot have just cosine pi x over L and the same function, right? Because we care about two distinct functions from this set. So we show one of them with cosine n pi x over L and the other one with cosine m pi x over L, and we're saying that n and m are not equal. And similarly, the other scenario is that you have both of functions are coming from the sine family. So for this scenario, again, you cannot have both of the functions to be the same. So you need to have two distinct functions, two distinct sine functions. One of them can be shown as sine of n pi x over L, and the other one sine of m pi x over L, where n and m are not equal. So that's it, right? So these are all the scenarios that we have for this infinite set of functions. And if we calculate the inner products that we have shown here, these 5 inner products, that's gonna be representing all the infinite number of inner products that you could imagine for two distinct functions from this infinite set. So our job is to calculate all these inner products and see if all of them are gonna be 0. If that's the case, that means that this infinite set is gonna be orthogonal on that specific interval that we are looking at. Okay, so let's start with the first category, category of 1 and another function from the cosine family. So the inner product of 1 and cosine n pi x over L. This is what we want to calculate. And by the definition, that's going to be the integral of the product of these two functions, which is going to be cosine n pi x over L. And these are the lower and upper bounds of these integral, defined by the interval that we are interested in, which is minus L to L for this specific problem. So if you evaluate this integral, is going to be L over n pi times sine of these arguments, sine of n pi x over L. And the lower and upper limits are going to be minus L to L. So if you substitute L and minus L into this relation that you have here, that's going to be, for L, that's going to be sine of n pi, because L is going to be cancelled out from top and bottom. And if you substitute minus L, then you're going to get minus n pi, because L, again, is going to be cancelled out from top and bottom. So you end up with L over n pi, which is going to be kept here. And then you're going to have two terms here, sine n pi minus sine minus n pi. And from the previous discussions that we had, we know that both of these terms are going to be 0. So that means that the inner product that we have here is going to be 0. Now let's look at the second scenario, in which we have one of the functions being 1 and the second function is picked from the sine family. So we want to calculate the inner product of 1 and sine of n pi x over L. So that's going to be, by the definition, the integral from minus L to L of the product of these two functions, which is going to be sine of n pi x over L dx. If you integrate this, you're going to get minus L over n pi times cosine of this argument, which is going to be cosine of n pi x over L. Again, lower limit is going to be minus L, upper limit is going to be L. If you substitute these values back into this relationship, you're going to get cosine n pi, because L is going to be simply cancelled out from top and bottom. And the second term is going to be, by substituting minus L here, you're going to get cosine minus n pi. So we know that the cosine n pi is going to be minus 1 to power n. And for those of you who may still doubt why this is the case, so if you have cosine 1 times pi, that's going to be minus 1, right? If you have cosine 2 pi, that's going to be 1. If you have cosine 3 pi, that's going to be minus 1. Cosine 4 pi is going to be plus 1, and so on and so forth, right? So that means we can find a pattern here, and the pattern is that if the integer multiplier is odd, then you're going to get minus 1. If it's even, you're going to get plus 1, right? So then this equation that I have written here on the left is going to be valid, because if n is odd, we're going to get minus 1 to power some odd integer, which is going to be minus 1. And if n is even, then it's going to be plus 1. So it's going to be minus 1 to power some even integer, which is going to be equal to plus 1. So all these kind of specific examples that I have shown on the right can be simplified into one single equation like this. So cosine n pi is going to be minus 1 to power n, right? So this is the identity that we have, and if we use it, this one is going to be minus 1 to power n, and this one is going to be also minus 1 to power n again. So let me explain this one too. So if we have cosine minus pi, that's going to be equal to cosine pi, right? Because we know that cosine of any angle, let's say alpha, is going to be equal to cosine minus alpha, right? So cosine minus n pi is going to be equal to cosine n pi. So again, both of these values are equal, and if you subtract one from the other, you're going to end up with 0. In other words, all the corresponding infinite pairs are going to have 0 inner product. And here we want to look at the third scenario in which one of the functions is coming from cosine family and the other one is coming from the sine family. So inner product of cosine n pi x over L and sine of n pi x over L. So n and m are independent, so they can be equal or unequal. So this inner product is going to be, by definition, the integral of the product of these two functions, cosine n pi x over L times sine n pi x over L, right, from minus L to L. So now here we have the product of these two trigonometric functions, and we need to rewrite this in a simpler fashion. So in order to do that, we can use this trigonometric identity shown here. So if we use this identity, then we can rewrite this integral as shown here. So we can rewrite this cosine times sine function as sine of addition of these two arguments, which is going to be n plus m times the rest, pi x over L, plus sine of alpha minus beta. So that means this is alpha here for our case. So it's going to be m minus n times the rest, which is pi x over L. And we have also a factor of half here, which shows up here out of the integral. And integral is going to be on minus L to L. So now it's much easier to deal with these integral. What we need to do is to substitute L into this equation. That's going to be the first term minus the same equation by substituting minus L. So if we do that for the first one, for the first term here, we're going to get, so this is the term that we can keep outside. So it's going to be minus L over n plus n pi. So for this term here, cosine, if you substitute L, you're going to get just n plus n times pi, because L is going to be cancelled out from top and bottom. So you're going to have cosine of n plus n times pi. And if you substitute minus L, then it's going to be pretty much the same, except you end up with a minus here. So similarly for the second term, for this one, you can keep all these constants outside, minus L over m minus n pi. And then just for this term that you have a cosine here, if you substitute L is going to be cancelled out from top and bottom, and you're going to get cosine of m minus n times pi, which is this term. And if you substitute minus L, then you're going to end up with pretty much the same term, except there is going to be a minus here because of the minus L. So now we need to evaluate this new equation, and it's going to be also 0. And the reason for that is that we said that cosine of minus alpha is going to be equal to cosine alpha, right? So if you look at here, for example, it's going to be n plus n times pi, cosine of that, minus cosine of just the negative of that argument. So they're the same. So if you subtract one from the other, it's going to be just 0. Similarly, for the second one, you have cosine of m minus n times pi, and the negative of that argument, which is having the same cosine. So this expression is going to be 0 as well. So at the end, you're going to get 0 for this inner product that we have shown here. So now let's look at the fourth scenario in which we have one of the functions from, basically we have both of the functions coming from the cosine family. And now, since they're coming from the same family, n and m cannot be the same. So by definition, this inner product is going to be the integral of the product of these two functions, cosine n pi x over L times cosine m pi x over L dx over this interval that we are interested in, minus L to L. So we want to rewrite this integral in such a way to be able to evaluate the integral. So we have the product of two trigonometric functions, two cosine functions, and from this trigonometric identity that I have shown here, cosine alpha times cosine beta can be rewritten as half times cosine alpha plus beta plus cosine alpha minus beta. And if you use this identity, you can rewrite this product of these two cosine functions as the summation of these two new cosine functions. So the first one is going to be cosine of, so alpha plus beta means this summation of these two arguments. So we're going to have n plus m times the rest, pi x over L, plus cosine alpha minus beta. So it's going to be n minus m times the rest, which is going to be pi x over L. So our integral is much easier now to evaluate. We have two trigonometric functions, two cosine functions here. So for the first one, cosine n plus m times pi x over L, the integral is going to be sine of this, right, multiplied by L divided by this term, n plus m times pi. So it's going to be this whole term here. And for the second one, integral of cosine, this argument is going to be, again, sine of this argument, sine of n minus m times pi x over L, multiplied by L divided by n minus m pi, which is shown here. So, and the lower and upper limits are going to be minus L to L. So if you substitute L and minus L for the first term, you're going to get, so this constant is going to be kept outside, L over n plus m pi, and for just sine term, you're going to get, if you substitute L, you're going to get n plus m pi. L is going to be cancelled out here. So you're going to have sine of n plus m times pi minus whatever you get by substituting minus L, which is going to be sine of n plus m pi multiplied by minus 1, which is going to be this term. And for the second one, you're going to get this one. So L over n minus m pi is going to be kept outside. For sine itself, you're going to get two terms, one of them by substituting L, which is going to be sine of n minus m pi. L itself is going to be cancelled out, so you're going to get this term. And by substituting minus L, you're going to get sine of n minus m times pi times minus 1, which is going to be this one. So again, you're going to end up with a bunch of sine terms here, and the argument is going to be just an integer multiplied by pi, which is going to be 0. Right? All of these terms, if you look at them carefully, you're going to see that all of them have a integer multiplied by pi. So sine of that is going to be 0. So this inner product is going to be 0, 2. And finally, we get to the last category in which both of the functions are picked from the sine family. So again, since both of those functions are coming from the sine family, from the same family, I should say, they cannot be, they cannot have the same index. N and m are going to be different because we want to look at two distinct functions from our infinite set, right? So it's going to be the integral of the product of these two functions, sine n pi x over L and sine m pi x over L. So again, we have the product of two trigonometric functions. We need to rewrite it in a more proper fashion, and we can use this trigonometric identity. Sine alpha times sine beta equals half times cosine alpha minus beta minus cosine alpha plus beta. And if we use this identity, then this product can be rewritten as what you can see here. Cosine of alpha minus beta, which is going to be n minus m times the rest, pi x over L, minus cosine, summation of these arguments, which is going to be n plus m times pi x over L. So the first one is going to give us this term, integral of cosine. This argument is going to be sine of the same argument times L divided by n minus m pi. And similarly for the second term, integral of this cosine is going to be a sine with the same argument multiplied by L divided by n plus m pi from minus L to L. And if we substitute L and minus L, we're going to get this whole expression shown here. So similar to what we did before, we keep this constant outside and we just substitute ln minus L into this term here, sine function, and we're going to get sine of n minus m times pi, since L is going to be cancelled out from top and bottom. And for the minus L, we're going to get also a minus right next to the argument here. For the second term, this one, we're going to get these two terms. By substituting L, we're going to get sine of n plus m times pi, and by substituting minus L, we're going to get sine of n plus m times pi times minus 1, which is going to be this term. And again, we are dealing with all these sine functions, the argument of which is just an integer multiplied by pi, which is going to be 0. So this inner product is also 0, and this was the last category that we wanted to look at. So basically all of the scenarios that we examined resulted in a 0 inner product. And what it means is that that infinite set is going to be indeed orthogonal on the interval minus L to L. So I have two more examples, example 3 and 4, but this video has already gotten too long. So what I'm going to do is to ask you to pause the video and try to work on this problem by yourself. I'm going to show you the result in few seconds, but it's going to be really helpful if you try to apply the same principles and concepts that we discussed in the previous two examples here and see if you can solve this problem. So pause the video and try to do your best. Hopefully you can solve it. If not, the solution is going to be shown to you in the next few seconds. And similarly, then I'm going to show you the example number 4, and you can pause the video and then you can come back and see the rest of the video with a very brief and quick overview of the solution procedure. Okay, so for those of you who were able to solve this problem, congratulations. So basically we have two classes of functions here. One of them is 1, the other one is this cosine function. So basically you have two scenarios. One of them is where you have just one as the first function and the other function is coming from the cosine family, and the second scenario is that both of the functions are coming from the cosine family. And you need to do basically the same calculations that we did for both of these scenarios. I'm going to just show you the calculation so that you can check your work. But it's pretty much the same. So here you're using the trigonometric identity for the case that you have two cosine functions. And if you do all these calculations, at the end you're going to see inner product is 0 for both scenarios. So yeah, so that's how you can show that this set is orthogonal on this interval. Now this is the fourth example, and I want you to prove that this infinite set is orthogonal on interval 0 to L. So pause the video please and start working on it. The solution is going to be presented to you in just a few seconds. So here is the solution procedure for this problem, and you can compare your work against what I have here. For this problem, it's going to be a bit easier because we have just one family of functions, and that's going to be the sine functions. So you just need to have one scenario to look at, and that scenario is going to be when you have two functions are coming from this same family, sine of n pi x over L and sine of m pi x over L. And n and m are going to be unequal. So if you do the calculations using this trigonometric identity, you can rewrite your integral in this proper fashion, and then you can calculate each of those integrals, and you end up with 0 at the end. So that's how you can basically prove that this infinite set is indeed orthogonal on the interval 0 to L.